All right, so we will be looking at the maximum and minimum values attained by a function of two variables. Let's let z be a z equal to f of xy be a function of two variables x and y. The first derivative of f of xy at a point P equal to AB is denoted by f prime of P, and it is defined to be the gradient of f evaluated at P. So it is the vector where the first component is the partial of f with respect to x evaluated at P, and the second component is the partial of f with respect to y at P. So you can think of that as a vector or a 1/2 matrix. Now this is the textbook that we are using doesn't use this notation f prime for this first derivative of f. So the text only uses the notation this notation for the gradient of f. So the gradient basically is the first derivative. And then the second derivative of f at the point P is the 2/2 matrix, which is denoted by f double prime of P, and it is this 2/2 matrix where the entries are the following. So here I have the second order derivative of f with respect to x twice. Here I have the second order derivative of f with respect to y twice. Here I have the second order derivative of f with respect to y first, and then with respect to x. Here I have the second order derivative of f with respect to x first, and then with respect to y. And now remember the alternative notations for this partials are fxx, fyx, fxy, and fyy. And so that's the second derivative of f at a given point. Now, if I want, I can emphasize that I'm evaluating them at P, because that's where I'm evaluating the second derivative. Recall that the mixed partials here, fyx and fxy, or these two here, they are equal under continuity assumption. Okay, so one way to remember this 2/2 matrix is that, you see, the first row, if you look at the gradient, right? If you take the derivative of the gradient with respect to x, then what happens? If I take the derivative of this with respect to x again, I'm going to get fxx, and if I take the derivative of this with respect to x, then I get fyx. Now in the second row, we are taking the derivative of the gradient with respect to y. So if I take the derivative of fx with respect to y, I get fxy. If I take the derivative of fy with respect to with respect to y, I get fyy. So the first row here is you can think of that as the derivative of the gradient with respect to x, and you can think of the second row as the derivative of the gradient with respect to y. All right. So the discriminant of the function f is denoted by d, and it is defined to be the determinant of this 2/2 matrix. So if I look at the f double prime of x evaluated at xy, then take the determinant, then basically the determinant would be fxx multiplied by fyy minus fxy multiplied by fyx. But these two are equal, so I can simply write fxy squared here. So this quantity here is known as the discriminant of the function f. Let's look at an example. Let's say that f of xy is x to the 4 plus y to the 4 minus 4xy plus 1. The partial derivative of f with respect to x is equal to 4x cubed minus 4y. The partial of f with respect to y would be 4y cubed minus 4x. Partial of f, second partial derivative of f with respect to x, again, so twice is going to be 12x squared. Second partial derivative of f with respect to y twice would be 12y squared. Second partial derivative of f with respect to x first and then with respect to y. So I take the derivative of this with respect to y, I get negative 4. Similarly, the second partial derivative of f with respect to y first and then x, it'll be the derivative of this guy with respect to x, which would be negative 4. So the first order derivative of f would be the vector consisting of the first order partial derivatives. So I have 4x cubed minus 4y here and 4y cubed minus 4x here. And the second order derivative of f would be the 2 by 2 matrix, where the first entry here would be the second order derivative of f, second partial derivative of f with respect to x twice, so that's 12x squared. The entry in the second row, second column would be this guy, 12y squared. The 1 2 entry would be the 1 2 entry would be, okay, so you take the 1 2 entry would be this guy, which is negative 4, and the 2 1 entry would be this guy right here. Now this two will be equal as long as the continuity assumption is true. So that's the second derivative, and then finally the discriminant is the determinant of this 2 by 2 matrix. So we multiply 12x squared and 12y squared, we get 144x squared y squared, and then minus the product of these two is 16, so that's minus 16. A matrix where, if I have a 2 by 2 matrix, if the off diagonal, so this is the main diagonal here, and the off diagonal entries are equal, that's called symmetric. And a matrix here would be called like this, is called positive definite. Remember, this is fxx right here, and if a matrix like that is called positive definite if at a point if fxx is positive there and the determinant is also positive there. Okay, so we don't really need the statement in red. Okay, so I'm going to stop here, and in the next video we'll be defining the local max and local mean of a function.